between are arguably less important than driving. Driving is all important. Now, you don't expect to find this answer in Wikipedia because it's not a property of Mountain View or a property of Los Gatos. This can perhaps only come out of blogs or something where people complain about the traffic.
Sir?
Yeah.
So like in this example only, when there are so many strings, how do we prioritize that typical and between are not important in driving is?
Yeah. So there are standard techniques in information retrieval which can assign weights to different words. But that's sort of in a background sense. Well, here are words in a big corpus. In general, frequent words are less help for narrowing down documents. Rare words are better. But that's a very weak signal.
So with like the last example that previous slide. So in the last example, previous slide, here we chose the word Albert and violin. There's Munich and suppose music. So it might end up showing a result about a music concert in Munich.
Absolutely.
So what are the prioritizing fundamentals?
Well, it's a function of both the query and the document. Right? So we'll see that through this talk. But this talk is only a 2-hour window. I mean, there are whole courses set up to do that. So the second query is more of the same in the sense that it's similar to the first query, but it's more evolved. There are certain things which are entities, Mountain View and Los Gatos. I don't mean any old mountain. I mean a specific town called Mountain View. So there's an issue of disambiguating the name of a named entity. But then I'm also looking for a target type, just like here I'm looking for a target type sign. So, and there are more applications than just search. So here I'm outlining only search applications, but there are more. So suppose you scan web corpus and you see that President Obama signed some bill. Now, maybe Obama hasn't signed so many bills yet, but if you generalize this entity to the fact that he's a senator and a politician, then aggregating over a lot of web documents, you see that, well, it seems like politicians and senators are in the business of signing bills all the time. That's what they do. Politicians sign bills. Or something refreshingly different, you see that Higgs hypothesized a new particle. And then if you lift Higgs to types like physicists and scientists, then it's easy to catch the pattern that, physicists seem to hypothesize. And then there's interesting questions. Do physicists hypothesize more or do mathematicians hypothesize more? So can you find that out quickly? Right? So today, you cannot play games like this on the web. You can ask literal queries, and already the web has removed a lot of speculation. So you're having a coffee table discussion about something or the other. Earlier, it could get away by wild speculation. Now you can't, because someone is going to whip out their phone and start querying Wikipedia. Right? So, but we can get further in this. We can answer this query. Does the web think mathematicians hypothesize more or physicists hypothesize more? So if you had a query language for probing this sort of small twig graph, you could do that. Now what's the use of all this? If we start learning patterns like politicians sign bills and physicists hypothesize particles, later on, suppose you see a combination of two sentences. Obama announced, and then the next sentence says he signed into law. Earlier, it might have been a difficult problem to understand that he refers to Obama because there could be other people mentioned with the same passage. Now, it's pretty clear that he is more likely to refer to Obama because he signed into law and Obama is known to be a politician. So this sort of linkage between noun types and verbs is another natural fallout from the kind of analysis that I shall describe. So let's get started with some of the basic plumbing we need to build this kind of a system. So here's a passage. The lack of memory and time-efficient libraries in the free software world has been the main motivation to create it. Now we look at memory. That memory is what I call a mention. It's a mention of something, some entity. And the spot is some limited token context around the entity. What's the width of the context? Well, I don't know. I mean, it's difficult to define that, and depending on the kind of algorithm you're using, it could be the whole document, it could be the whole website, or it could be 5 words around the token. It's hard to say. So we'll keep that a little fuzzy for the moment. Now, if a human reads this, it's immediately clear that memory does not refer to your reminiscences of your childhood. This is a computer artifact, and that's clear from the context. Similarly, it's clear that library here has no connection to books and shelves, that it refers to software. So our goal would be to first spot those red tokens, and then second, do the correct interpretation of each of those red entities. So let S0 be the set of all interesting spots on a page. Again, what's interesting is very vague. And let small s be one of those spots, like memory in the context of those underlined words. Now, this may look obvious to a human, but it's very complicated for machines, because this involves a massive similarity join between a billion-page corpus and a large entity catalog. For example, Wikipedia at the time of preparing this slide, which was ages back, had 2.5 million entities. Now it has over 4 million entities. And somewhat more number of lemmas. So New York may be referred to by two different lemmas. And about 7 billion lemma tokens. So as you scan the corpus, pretty much any token matches something or the other. What matches are significant enough to pull up as a spot and disambiguate is difficult to decide. For example, if you look up the token library, in Wikipedia you would find things like a collection of books, a collection of subprograms, electronic library of components, collection of molecules, the Library of Congress in the US, or an episode of the Seinfeld comedy, which was called The Library. It's also the name of a station somewhere. Station called Library. So for a machine, it's pretty difficult to narrow it down. And then the way you're scanning it also decides a lot of things. So you look at only York. York could be various things, but New York is fewer things. It could be a state or a city. And then if you suffix it by New York Times, it's a different thing entirely. So how you scan it, how you delimit what you think is an entity, and then you look up your catalog, and then you say, well, I think in this case, by and large, New York Times is in the newspaper, and there's no point breaking it down further. But there could be other cases where things are more murky. You could have a whole document or a passage which talks about some decision by, say, Kolkata University. And then later on it says, university officials said. And now this university means Kolkata University, not other places. Right? But that's a little dangerous, because what if in the same passage there is also a reference to Kolkata University? So it's tricky to do this kind of codef or reference resolution in the passage. Okay. Now, but the next step is, once you've identified that there's this yellow span or a red token I'd like to disambiguate, now we have this problem of choosing between multiple competing entities. So let S be a spot which we think is a mention of some entity in your catalog. Let gamma S be the set of candidate entities. So for John Smith, there may be 200 John Smiths. For New York, there may be only 2 New Yorks. For Albert Einstein, there may be 3. Right. So actually yesterday in the airport, someone signed up for a cab in front of me in the queue who told the counter person that his name was Saddam Hussein. That must be difficult. So anyway, so also, given your catalog is always incomplete, one of the spots may be best left unconnected. You'd say that, well, here's John Smith, and I do have 200 John Smiths in my catalog, but I don't think this John Smith is any one of them, so I'll leave them unlinked. Sometimes you want to do that because you think your catalog is incomplete, or other times you want to do that because the surrounding passage does not give you enough confidence. The end story is the same. You may leave a fraction of spots unconnected, and we call that NA, or no attachment. Other people call it null or nil, many others. So, for example, most people that are mentioned on the web are missing from Wikipedia, because Wikipedia only lists famous people. But if there is a new star or galaxy or constellation found by astronomers, you can be sure that within 20 minutes it will be in Wikipedia. So already there's this interesting structure that different types of things are incorporated in your catalog at different rates. And while deciding whether you want to NA some spot or not, prior knowledge of that might help. So by and large, the predominant signal that you use to link entities is the local context. So you see a passage like this. On first getting into the 2009 Jaguar XF, It seems like the ultimate in automotive tech, a red backlight on the engine start button pulses with a heartbeat cadence. So of course, if you wanted to annotate Jaguar, it's a car, it's not the animal or it's not the sports team. And that's partly easy from the green words. There may be some confounding word like pulse or heartbeat which may drive you towards the animal. But there are enough machine learning techniques today which can learn to ignore the red words and pick on the green words and do the right thing. That's not good. So pictorially, I'll represent this as a document with a bunch of spots in it. A spot is the actual mentioned word Jaguar embedded in that line, which is some of the surrounding context. That's my pictogram for a spot. And then this funnel maps to the set of entities which are candidates for this spot. So this is Jaguar, here are the 3 candidates. Here is John Smith, here are 200 candidates. Along with NA always lurking out there. And one candidate is gamma and one candidate here is gamma prime. So I now have this assignment problem where every spot has to go to 0 or 1 entry inside the funnel. Is that clear? That's my entity annotation problem. Now, what I've shown here is codified as some kind of spot to label compatibility. If I'm talking about engines and acceleration and smooth drive and so on, then the car is better for this guy. If I'm talking about Ford, and here is Harrison Ford, and here is the Ford Motor Company, I could pick anyone. But clearly, these are not independent funnels, and that's what I'm coming to next. If you look at the string Michael Jordan on the web, predominantly it's Michael Jordan, the basketball player and celebrity. But there is also a lesser known Michael Jordan who may be more of a celebrity in this institute, who is a professor of statistics at Berkeley. And similarly, if you see Stuart Russell as a name, Stuart Russell might mean the British movie actor or the British thespian. But if you see on a single page both Stuart Russell and Michael Jordan mentioned, you can be pretty much sure that these are the 2 professors at Berkeley, one in statistics and machine learning, the other in artificial intelligence. Just because they mentioned together on the page, there's no good reason to mention an American basketball player with a British actor on the same page, as much as mentioning 2 professors in the same department on the same page. So here's a similar example. So I see Michael Jordan also noted for his product announcement, endorsements. He fueled the success of Nike's Air Jordan sneakers. The Chicago Bulls selected Jordan with some overall pick, etc. So Michael Jordan here could be the basketball player, or it could be the American actor, or it could be an American researcher of statistics. Chicago itself as a substring is a movie. Chicago Bulls is an American basketball team. And Air Jordan might be a reference to an airline from Jordan, or it could be a line of Nike shoes. Now, each of those spots presents to us an assignment problem. So it's a 1-to-1 out of many assignment problem. And we represent that by saying that y sub s, remember s is a spot, and y sub s has to be picked from the candidates or null. I don't want to link. I can do that independently for all of these guys, but you realize that there is no good reason a passage should talk about an American actor together with a basketball team and an airline. Except for these weird stories where the American actor starts acting as a basketball player and takes a flight somewhere. That's very important, right? The more natural explanation for all these strings is that we're talking about the basketball player who played in a particular basketball team, no movie is involved, and that he endorsed a particular shoe because Nike appears. So this Jordan is not annotated with the basketball player himself because it's close to Nike and Nike mentions shoe. So that's a complicated line of reasoning that humans do effortlessly without thinking when they read this kind of a passage and they have to understand the meaning of the blue tokens. The question is, how do we model, at least crudely or partly, how humans collectively assigned a label to each spot without trying to do that one at a time, independent of the other labels in the same page. So is the setup clear?
Yes.
So we show that pictorially by souping up the earlier diagram. We still have those funnels. And the issue of spot to label compatibility is still very much there. If you look at this sort of a passage, then surely, whether this Michael Jordan is a basketball player or not, we need to look for neighboring features like Chicago Bulls, which hints at a basketball player, rather than a statistics researcher. So the issue of local compatibility is also very much there, still. But the new game is that if you choose an entity gamma for S, like Michael Jordan basketball player, and Chicago Bulls, you pick a sports club rather than Chicago the movie, then it must be the case that in some vague semantic space, these entities gamma and gamma prime have embeddings shown as those vectors, G of gamma and G of gamma prime, such that those vectors are close together. So now think of the problem as follows. Depending on your choice of assignment from the spots to some entity in each funnel, for certain bad choices, you are going to get vectors here which are all over the place. But if you make good choices in each funnel, then their corresponding vectors are going to be close together. Okay. So that completes the diamond or the circle, if you will. We come from a single document, and hopefully the document is coherent topically. Therefore, the entities it refers to has to be closed in some semantic space. Yeah?
What is the vector space represent?
Right. So that's a good question. It's a complicated question. So in the first work I'll show, we embed these entities as vectors in a certain feature space, which is defined from, say, Wikipedia. For example, you might say that every axis of this space is a category in Wikipedia. So if this is Michael Jordan and that is Stuart Russell, and these are professors at Berkeley, then their vectors will be very close together in terms of the categories they interact with. They interact with research, papers, maybe patterns, students, those categories will figure high in these axes. But that's not a perfectly satisfactory answer, because I started out the talk saying the catalog is always work in progress, and therefore depending on its category structure for this embedding may not be the right thing to do. So in the last year, Google has done some work on finding embeddings in an unsupervised way for entities and categories. So I don't have time to go into that, but that's one way of discovering the embedding rather than designing it. Like, okay, so now we're looking for some sort of a collective objective function which not only maximizes the compatibility within each funnel, but also maximizes a global coherence measure across the chosen entities. So I won't go into the details of what that exact objective looks like, but once you get the idea to do this, anyone can sit around for a couple of days and come up with a bunch of objectives. Before we jump to algorithms for trying to optimize such objectives, we need to verify that if the objective value is high for certain configurations, that leads to better analytics. So as a matter of research methodology, at this point one shouldn't jump to optimization algorithms, one should instead look at a bunch of pages, get them hand annotated, and in fact distort or perturb some of the annotations so that they go wrong places, evaluate the designed objective, show the page to humans, and try to correlate the objective with the perceived quality that humans find in the annotation. And here's the result. So on the x-axis, so each dot here, you could ignore the lines for the time being. Think of it more as a scatter plot. So it's a scatter plot with two axes, and there are 6 documents represented by 6 columns. There are 6 sample documents. The x-axis is the relative value of the objective. So we designed some magic objective, and we told people to annotate the page. Then we artificially scrambled a bunch of annotations so that they went to the wrong entities. And for those various samples, we calculated our relative objective. Meanwhile, we gave the perturbed page to yet other humans, and told them to evaluate if the page was, to what extent the page was correctly annotated. And the goal is to see if there is a positive correlation. There is a very good positive correlation. For every page, you see that the bigger our objective, the more people think it's accurately annotated. So now there's enough ground to start chasing algorithms for optimizing that objective. So we had, so this is not a very benign objective, it's a generalized quadratic assignment problem because every pairwise interaction of entities is concerned. And we have one hill climbing algorithm and one integer programming rounding algorithm, which is probably great. But both of them sort of work comparably. And here is a recall precision curve for various algorithms trying to do this collective annotation. So recall is the fraction of entities in ground truth that you actually successfully annotate, but perhaps wrongly. And the precision is what fraction of your annotations are correct. You have heard of that yesterday, perhaps. So the more aggressively you drive your annotation agenda, the more mistakes you are likely to make. So typically these graphs are all sort of negative slope for any system. So we manually annotated about 20,000 spots in web documents, and here's our local algorithm, which already turns out to be superior to two very well-known systems from the literature. So the Microsoft system, push, recall, and loss precision. The Milner-Witten system from 2008 was more on the side of precision, so higher precision and lower recall. And our local system itself beat them, and then the collective algorithm had a much better recall precision envelope. So this really shows the value of making collective judgments of spot to entity assignments throughout a page. Any questions? So this is all fine, but we are doing all this with regard to an established entity catalog like Wikipedia. These experiments are all done with Wikipedia. And the problem there is that Wikipedia is tiny. There are so many John Smiths who would like to figure as a response of web searches who are not in Wikipedia. So we can think of Wikipedia with its, so these slides were made later, so I caught up with the world. About 4 million hid entities, so these are famous people and constellations or galaxies or important companies. And the additional value of Wikipedia comes not from just being a catalog of entities, but also having this large corpus of pages, where there are these links from the unstructured or reference corpus into the entities in the catalog. And the reason why it's so valuable is that this gives you example text in which references to these entities are embedded. So that you can generalize from that reference corpus to the web corpus. You say, well, if I knew where Albert Einstein was referred from Wikipedia, let's try to learn general patterns and try to spot mentions of Albert Einstein all over the web. That's easy to do because you're given so much nice clean text to do that. The difficulty is that this third generation star or stars of Wikipedia is embedded in a far more nebulous space of entities, which is forever forming. It's like, previous with its 40 million entities. An entity starts out being a very fledgling star somewhere. These are obscure tail entities. There's some young novelist who has just written 2 books, and that's a node in previous, connected to the 2 books. The author or their friends, they may not have taken the care to have tagged that node as a writer or an author. Not so much care is taken over previous as Wikipedia. And it's much more difficult to find good connections to other entities for the fledgling new entities, or to type them properly. So you look at this new node with 2 connected nodes, it's very difficult to know that this guy is an author. So our goal is to start from the well-developed part of the galaxy and then generalize our annotations to the fledgling stars from the green one to the yellow. The green star here is very well connected. It's trivial to find out what kind of object it is. Physicists or scientists prove. Whereas the yellow star is just been formed. It has 2 or 3 links, so maybe no links. Can I even hope to spot appearances of the yellow star in a payload corpus like the web? So that will be the next segment of the talk. And we have help from various quarters. Of course, the predominant way in which we connect entities to mentions on pages is still local context. For example, here's a candidate entity. In the knowledge graph, it has a neighborhood which I call NE. And here's a passage. I'm trying to decide if this black block text is a reference to that black entity here. Now, of course, I'll feel more confident about doing that if in the passage there are also a mention of a green entity and a mention of a red entity which are close to the black entity in the knowledge graph. That's a standard signal. And the person's name is Anthony John Williams. Here is a passage which unambiguously refers to him because of matches with chemistry and ChemSpider in the neighborhood. So ChemSpider is relatively unique. So coming back to your question, that if a term is very rare and it matches, that's a stronger signal. And chemistry is a weaker but still significant match between the graph neighborhood and the passage. So this is fine. It will snag a certain fraction of previous entities out on the web. But there are many other cases which are not so fortunate. So here's the second one. So this John Williams is actually a sports person. He's an American football player. So the linked neighborhood is not bad. But if you look at the passage here, there's not a single text match between the surrounding text and the graph neighborhood. A human finds heuristic matches out of text. Well, if this guy is a football player, that links us to sports. And if you see things like quarter and running back and touchdown and Steelers and Packers and Colts, an obvious clue about sports stuff. But computers can't do that very well. Why not? This is one of the final frontiers of understanding our brain, which is, so concepts in our mind are in what's called a small world graph. So what's a small world graph? It has millions or billions of nodes in it. However, the diameter of the graph is very small. From any concept to another concept, you can go around very few hops. And therefore, the problem is that no path length or distance-based pruning works. So we need very smart prioritization techniques on the graph to find out promising paths. So to a human, it's clear that both the passage and the target node are converging on sports teams, but it's not easy for a machine to do that with the explicit representation of free. So the nice thing is that if we knew that this John Williams is a sports person, or we could type this John Williams properly in the passage, this application becomes pretty easy. So the type interpretation was missing in the previous picture. Each type has to be used more intelligently. Now, this will sometimes help and sometimes not. It turns out there is a second basketball player who was also called Michael Jordan. And he got so frustrated with being always mistaken for the big Michael Jordan that he changed his name to Michael Hakim Jordan. So most of the time, disambiguating the type will let you distinguish two John Smiths, at least in a particular context. But sometimes not. But that can come from other quarters. The third case is even more difficult. So we have the daughter of Puritan Minister Reverend John Williams and his wife Eunice. So this is a tail entity. It's just starting out on freeways, not to care about this entity. And in fact, this node in freeways does not even have a link called type. So no one has bothered to go in and register the type of entity in freeways. We do know that this John Williams got his degree from Harvard and has a child called Eunice, long middle name Williams. And in fact, if you look at this passage, this Eunice Williams is not that. Actually, this is this person's daughter with a different middle name. So the text match is weak and unreliable, and we have little typing information. So the question is, across this spectrum, how far can we succeed in expanding from those well-known Wikipedia entities to typing the previous entities and finding their mentions in web text? So the goals are twofold. One, take new entities in previous which are not in Wikipedia. So I'm using Wikipedia and previous sort of symbolically as small and well-developed subset of a big and fledgling universe. So I'd like to look for previous entities which are not in Wikipedia and associate a well understood type with every node in F minus W. And second, in the payload corpus, like a new big web corpus, I'd like to identify all mentions of entities in F minus W as well. Entities in W or W intersect F is easy. Believe it. Entities in F minus W are difficult because we don't have enough information from their knowledge base here. So we thought about this for a while and we came up with this tripartite assignment. So there seem to be these three things involved in this setup. There are the entities, and there are these mentions in context like our old spots, M1 and M2. Here are entities E and E2. And there's a many-to-many relationship between those. So the mention M1 may be of an entity E or entity E prime. Mention M2 could be of entity E or something else, or not. And then each entity, this is an entity in pre-base, has a bunch of candidate types like T and T prime. This Michael Jordan node in pre-base, who is not as well known, may be an accountant or a painter. I don't know which one. So there's this three-part objective, and to understand what each entity has and what entity is mentioned by mention, I need to actually close the triangle. That's the important insight we had, which is that if I know nothing about the entity, but the entity is talked about as hitting the ball and scoring a goal, I don't care who the entity is, it's a football. Or something similar. Maybe a field. So somehow there's this direct connection between types and mention contexts, and entities are sort of incidental in between. And we need to score all three edges of this triangle. What are the three